that down so people can see what's up here. Okay, so today we're going to move through this stuff pretty quickly. If I'm going too fast, stop me, slow me down. But a lot of this is going to be pretty basic. It's going to be, should be a review in terms of just frequency tables, exploring data, graphs, things along those lines, serving as sort of kind of the basis, very basics of some stuff that we're going to go through or work through throughout this semester. So we'll talk about frequency distributions, central tendency, variability, shape of sample distributions, things along those lines, and then finish up with some figures and sort of how to display graphically some of this stuff. Okay, remember that as we get into sets where we're actually using actual data, don't be scared to use graphical representations to help communicate your answers and things along those lines. Okay. So first thing we're going to touch on, work through frequency distributions, right? This isn't new information to anybody. We're just going through tabulating individuals located in different categories. You'll see this in any paper that you pull up. What we're trying to do is just kind of synthesize and communicate oftentimes characteristics of our data, right? So we're looking at demographics and background characteristics, things along these lines. If we got a good frequency table, it's going to show us clustering, your spread of scores, position of one individual relative to somebody else. I can go through and say, okay, if I'm looking at this distribution, I say this person is from the Southwest. If it's a distribution of samples or regions of the United States where people have residence, you say, is this a common occurrence? Is this an uncommon occurrence? Things along those lines. Okay. Components of our frequency distributions. We have our whatever our X here, whatever our category is. These are the categories that are making up our scale, and then we generally have some sort of frequency or number, right? It could be proportions, it could be percentages, it could be counts. There's no hard and fast rule for this. Like anything else, as you're going through putting these together, your goal is to say what makes the most sense, right? What most effectively communicates the information that I want my readers to have, and sort of using that to go through and put together your frequency tables. Here we have some what looks like an ordinal variable here with categories 5, 6, 7, 8, 9, 10. You know, this might be something that we would use as a more continuous variable with the frequency here. Here we've got a table looking at racial ethnic background, right, with different categories and frequencies going on here. Not news, but just sort of thinking about what we're trying to accomplish, right? And again, people do weird stuff with these frequency tables sometimes, and you look at it and you're like, well, that doesn't make a lot of sense, or that's confusing. That's a bad frequency table. You want to go through, make sure that it's in everything that you do, that you're communicating information efficiently and effectively. Okay. So these are just individual categories, right? These are just individual groups that we've placed people in. But sometimes when we get, and want to create frequency tables for variables that are inherently continuous, right? If there's an infinite number of possibilities on a continuous variable, we have to have some sort of strategy for displaying that in a frequency table that doesn't involve having every single observation that we've made in a sample. And so what we do is we create some group frequencies, okay? With our grouped frequency tables, what we want to do is we want to develop a class interval, okay? A class interval is sort of how many, sort of what the limits are for grouping things into categories, okay? Main thing here is you want your intervals to make sense given whatever it is that you're measuring, okay? So, Layla, what is the class interval? So here we've got a group frequency table looking at income for people who came in for study of PTSD and chronic pain, accident survivors. We go through, ask them for their income. We obviously can't put like every value that people have in our frequency table, so we've created this here. What is our class interval for our frequency table?
9,599.
Close.
10,000?
10,000. Okay. So our class interval here is 10,000. All right. But what we have is we've put our class interval into individual bins. Our bins divided by upper and lower limits. Amelia, what are the upper and lower limits for sort of some of these categories here?
The lower limit for each one would be like, let's go with the 70,000 one.
Yeah.
Lower limit would be 70,000, upper limit would be 79,999.
Exactly, right? So we've got, our class interval is 10,000, right? And our upper and lower, and our bins are sort of lower bound, upper bound that capture each one of these, okay? So again, pretty straightforward stuff, but some things you should think about in terms of developing these group frequency tables. And these are general recommendations, they're flexible, but things that you should be thinking about when you're putting this stuff together. Rule number one, distribution should have about 10 bins probably. Now this is going to vary from case to case, you know. Sometimes you're going to have more, sometimes you're going to have less. But if you have more than 10 bins without a good reason, there's a good chance your frequency table is going to be too complicated, right? And you're going to be cutting things too thin. If it's less, you've put people in the same category that may not be comparable, right? If my class interval for income is $100,000, I'm putting someone with no income and someone who makes $100,000 a year in the same bin. Those two people don't go together, okay? And so wanting to think in general about 10-ish, right? Now that's not a magic number, it's not right or wrong if you have more or less, but it's something that you want to be thinking for in a true continuous variable, okay? Rule number two, class interval should generally be divisible by a simple whole number, okay? Your class interval, you don't want to have weird class intervals, right? So my class interval is 13. Probably not, right? 10, 5, 20, 100, depending on what the scale is, right? Having some reasonable, intuitive, even simple whole number going in. Rule number three, all your intervals should be the same width and cover the same range of scores so that each category only, or each value only fits into one category. Okay? And when we're talking about real upper and real lower limit of our bins, real lower limit, the smallest value falling in the interval, real upper limit, the largest value. So if we go back here, my real lower limit for category 2 might be $999,000 or $9,999.50, right? That would round me up into this bin and count them here, right? And so my lower limit is 10,000, but the real lower limit is that 50 cent that rounds up or down. Real upper limit for my first bin here, $9,999.49, right? Now, it's not often that we get deep into the weeds and sort of that level of stuff, but you could have certain situations where it comes up where that real upper and real lower limit starts to make a difference, okay? So what if I would have set my upper and lower limits of my bins to 0 to 10,000, 10,000 to 20, 20 to 30, 30 to 40? What's wrong with that?
You're overlapping.
I'm overlapping, right? And so if I make exactly 10 grand a year, where do I get counted? Yeah.
The 10 to 19.
Okay, yeah. And so, but this is one of the things, and you'll see this sometimes in a frequency distribution, your upper and lower limits of different categories will start to overlap, and then that starts to get confusing on where people go. Okay. Yeah.
If you, let's say you only had literally 2 people that fell in the bottom 2 bins, would you consider expanding your interval class instead of going in 10,000, doing 20,000 jumps, or does that matter?
Right? And so what you want, this is nice, right? So I decided to, with this frequency table, create bins of $100,000, right? And I've got some reasonable representation moving up here. Now that's not to say you might not have a category with 0 people in it. That's fine. Now if you've got a bunch of categories with 0 people, you might want to think about how fine grained you want to go through and cut this. Okay. So again, these are general rules, but things to think about as you're putting together your frequency tables. Okay. And our last rule here: upper or lower limit or bin should be evenly divisible by the class interval. Okay. So if my class interval is 10, so I've got 0 to 9, 10 to 19, or 1 to 10, 10 to 20. My upper, my lower limit is divisible by my interval here, right? So if I say here 10 divided by 10 is 1, we're going to have 20 divided by 10 is 2. So everything kind of makes sense here. If we decide to go 1 to 10, my upper limits are divisible by my class interval, right? So these are just things that you should keep in mind so your frequency or your group frequencies don't get all over the place. Okay. So here's our group frequency table. So what I'm doing is I'm documenting. I got a sample of people who've been in accidents, right? And I'm interested in documenting how, after their accident, how many miles a day they drive, right? And so I say, okay, this is my frequency, group frequency distribution. Evelina, yes. Okay, I was close. I got like the first two. Evelina, is this a good or bad frequency distribution here?
Well, if you got like I think it's good.
Okay. What might be, if you had to criticize it, what might be a problem with this?
Well, like what would you do this for, like 1.4 or like anything between a 1 and a 2, where would that go?
Okay, right. And so then we would start thinking about real upper and lower limits, right? So if 1.2, if our real upper limit for this bottom bin is 1.44, out to infinity, right? Then we go through here. What's the other thing that's problematic with this, Haley?
Most of the scores are towards the bottom.
Okay, most of the scores are towards the bottom. What else, Emilio?
There's a lot of zeros, and you're missing quite a few categories.
A lot of
so you could
zeros,
just
missing quite a
condense them.
few. Right, what do you say, John?
Yeah, I was gonna say the same. Looks like you're missing like between 15 and 19 on the table.
What I would have done, I don't have enough bins, right? My class interval here is too small, right? Is there a meaningful difference between someone who drives 6 miles a day and someone who drives, or 7 miles a day, and someone who drives 8 miles a day? No. I've got a ton of, we're assuming that these dots mean that things are continuing up, right? I've got 20-some bins here. My class interval is too small, okay? I've diced things too thinly. These aren't probably aren't meaningfully distinct differences. If we're talking about miles driven a day. If we're talking about miles ran a day, maybe, right? But for the variable that we're looking at, we've cut this too thin. Right? Kate, what about this frequency table here? Is that good or bad?
I would say bad.
Yeah, why is that?
Because the interval or class interval changes. So like it's 0 to 50, and then like if you get up there, there's 100.
Yeah. Okay. So my class intervals aren't equal, right? This is my class interval here is 50, 50. That's 100. Yeah. We skipped some stuff in the middle there, right? What else is going on with this? What do you think, Laura?
I think it's too big.
It's too big.
Yeah, the class intervals are too large.
Yeah, class intervals are way too large, right? I'm saying the person who drives 0 miles a day and 50 miles a day, those two belong in the same group. That's probably not accurate, right? A lot of stuff going on with this. Intervals too big, intervals inconsistent, intervals aren't mutually exclusive, right? I've got gaps in here. This is kind of a poor showing, right? Here at least we were systematic and kept everything the same, but we just cut it too thin. This has a ton of stuff going on. What about this one right here, Amanda? What do you think?
That's better, but the class intervals aren't remaining consistent.
Yeah. Well,
it's not easily divisible.
there we go.
It's hard to pick out
Right.
what groups.
Yeah. My class intervals are actually consistent, right? I've got a class interval of 20,
It
right?
doesn't look like it.
Yeah, so we've got 20, 20, 20, 20, 20. So, but I've got weird, my upper and lower limits of my bin are weird, right? And so it's functionally, you can make an argument it doesn't make any difference, but visually in sort of communication, it's hard, right? Because you're like, what's going on, right? And then we also have gaps, right, where we haven't, or no, we don't have gaps, but it looks like we have gaps. So technically we're all right, it's just our class interval isn't divisible by our upper or lower bin, and it throws the whole thing off, makes it look weird, okay? People see this? All right. What about this one? Do we like this one? What do you think, Nick? Do we like this one? Yeah, this one's pretty good, right? We've got a class interval of 10. We've got upper and lower limits that don't overlap here. Our lower limit is divisible by our class interval, right? We've got reasonable representation. When we get up here, we got a 0 value. No one reported driving 90 to 99 miles, but that's fine. We have, 80 to 89. What we've done here at the top is something we've called, we would identify this as censored distribution, okay? Censored distribution means that, boy, once we get to 90 to 99, and then we have 3 people in our sample who are driving a lot, right? Now, if I were to continue to go up in 10-unit intervals, I might have to go several categories before I captured the next person and several more. So then we've got a bunch of zeros going on. And so what I did with this distribution is I said, okay, if we get people driving 100 miles or more, we're just identifying those as people who drive a lot. We're grouping them into a common category. And so this can be a good device for frequency distributions. It causes problems in terms of if we've actually measured this, right? If we've actually measured miles driven on, let's say you got to choose one of these scales, we lose information here because you could drive 300 miles a day or 100 miles a day. I don't know which one. A problem with censored data, but sometimes we'll run into this stuff. Okay. Questions with this?
If you do run into that, like I said, if, let's say we have someone at 300, would you have to state, like in the figure explanation that, you know, it was significantly different, or?
I wouldn't worry about that. I mean, this is just a frequency table. This is just descriptive stuff. This is just giving your reader, helping your reader qualify the characteristics of your sample, right? Now, if we want to go through and run analyses with this, there's certain types of techniques that deal with censored data. That gets a little bit beyond what we'll cover this year, but one of these things to keep in mind and think about how we measure data, how we recording things, so on and so forth. Okay. Other questions? Cool. All right. Frequency distributions in SPSS, pretty straightforward. Show of hands, who here has used SPSS in the past? Okay, everybody. Randy, you haven't?
I don't think so.
Okay. It'll be fun. What I'm going to do when we get into actual data stuff, I'll go through, post a couple of screencast videos that sort of walk you through the SPSS interface and things along. It'll be easy to pick up. Nice thing about SPSS, you can run things off of pull-down menus that are pretty intuitive. The display is pretty slick. But if we're going to get frequency distributions in SPSS, we go to Analyze, choose Descriptive Statistics, choose Frequencies, and then we would take whatever our variables are, plug these in. Frequency tables are limited categorical data. In SPSS, if you don't have your data, if your variable identified as a categorical variable, it might not show up for you to go through and punch in there. So again, when you're indicating your variable type, sometimes you have to make sure that it's the right type, otherwise SPSS won't read it in. But this is how you would get a frequency table. And here is what SPSS output looks like. Many of you are probably familiar with this. So if we look at, here we've got frequency distribution of employment. We've got 57% of our sample reporting unemployment, smaller, about 7% reporting working 1 to 10 hours, about 10% 11 to 30, about a quarter over 30, and then we've got 1 missing value in there. Okay. Here, looking at marital status, again, frequencies, percent, valid percent. What does this valid percent mean? Any ideas?
It includes only the valid responses, so like the missing data.
Yeah. So you see we've got 10 items, 10 values that are missing. Your percent will calculate the percentage out of the total number of observations. Valid percent calculates the percentage out of the number of values that are available there. Okay. And then cumulative percent is sort of how many people as you're sort of continuing up. So here, 35% or about 30%, 36% of people are reporting being separated or married. 45% reporting being divorced, separated, married, so on and so forth. Okay. Questions with SPSS or output there? You won't have to worry about this. This is just kind of showing you how you can get some of this data from this statistical program. Okay. Other thing I'm going to integrate in this year is showing you how to do some things in Stata. Again, talked a little bit about that the first DSS. Or if you're sort of use it a little bit, start to know what things to ask for, I can just type in FRE, gender and race, and then it just gives it to me right there. It actually considerably faster once you get the hang of stuff, and you can just be like, oh, I wonder what this is, FRE, gender, race, and boom, pops it up right up here, right? So we see number of men, women, about a third men, 2/3 women here in this sample that we're using. Racial ethnic identity here, looks like we don't have any missing values, so just another way to go through with a different program and having you call that stuff up. Okay. All right, questions about frequency distributions? Cool, all right. Gonna jump into central tendency here. Oh yeah.
Sorry to backtrack,
Nope.
but for cumulative percent, you said that means that, so 29.8% say that they're married, and then 35% say they're married and separated?
Well, we're just, if this were some sort of cumulative, like sort of linear sort of grouping of things, what this cumulative percent doing is it's, because in SPSS I code, this is 0, 1, 2, 3, 4, it's just giving my variable names here to help me interpret stuff, right? So this would say you have 29% or 30% of your sample set at a 1. You have 35.7% reporting 1 or 2. This one is going to be the percent endorsing 1, 2, or 3. We don't worry about this cumulative percent a whole lot, but it's kind of one of those things that that's provided that you can go through and interpret. Sound good? Cool. All right. Central tendency, right? This is our way of going through and identifying some sort of middle score, okay? What we're trying to do here, and keep this in mind, is we're trying to say, what is a single score? What is the single value that best typifies the middle of my distribution, okay? What we want to do is find a score that's most representative of our entire group, okay? This is most commonly what we're using in terms of doing between within group types of comparisons, wanting to find what's my best representative score for this group, what's my best representative score for that group, and then looking at those two to see if we have any differences, right? What complicates this is there's no single method, no single best method for determining central tendency, okay? This is going to be a common thing. You're going to have in your toolbox 2, 3, 4 different ways to do something. Your job is to find out and determine, okay, what's my best way of approaching this stuff? So, Kate, where's the center of this distribution?
At 100.
At 100, right? This one's pretty easy peasy, right? 100, right in the center, that's fun, okay? Hey, what about this one? Where's the center of that distribution? Maybe about -1, right? I mean, I could say this is, but I've got kind of more people over on this side, right? But then we've got people, and so this starts to get a little bit more difficult. John, what about this one? What's the center of that distribution?
I guess it's like a bimodal, so it probably depends. I guess it could be like either of the peaks, or
What's that?
it could maybe be like either of the peaks, or it's like bimodal. So
You only get one.
I'd say probably closer than to like 150-ish.
150-ish, right? But again, if we're trying to look for the single score that best typifies our sample, very few people are actually right there, right? So if we're looking at the mean, right, it's probably right there, but then we've got a score that doesn't actually reflect very many people in the sample, right? If we're looking at body mass, what do we probably have going on here? What might be your hypotheses? What do you think?
That most people fall between like 140 and 150.
Okay. Well, so what type of what might produce a distribution like this if you're measuring people's weight? Any ideas? Yeah.
Is it gender?
Probably, right? I would guess we have a gender effect going on here. Probably we have women and probably we have men, right? And so anytime you're going through and you're looking at a distribution, you see a bimodal distribution, one of the first things you should be thinking about is, have I actually captured two distinct populations in this distribution, right? This is gonna start to make you think about, boy, we got something that's very clearly bimodal in here. Maybe there's something that I'm not thinking. I've identified this as a population, which if my population is human beings, fair enough. But probably what I've got is probably two distinct populations in here, and so I might want to start thinking about how I go through and analyze this stuff. Does it make sense to combine these two groups together? Now, combining men and women might make sense in some situations, but maybe if we're looking at a test of mass, right, or eating pathologies or something like that, right, maybe it's important to split those up, because otherwise our data is going to get kind of funky. Okay, I see this in my intro psych class. Often, if I'm looking at quiz scores, I get kind of a bimodal distribution. What's going on there? What are my two populations? What do you think?
Slackers and the people who are actually doing the reading work.
Yeah, people who prepared for the exam and people who didn't prepare for the exam, right? We see a sort of nice spike over here, and we got another much lower spike over here, right? So again, one of these things, just by looking at distributions of your data, can start to develop hypotheses about what's going on in these data, what might that mean, so on and so forth. Okay. Choice of our measure of central tendency determined primarily by the shape of the distribution and the type of data that we're working with. Okay. If we're talking about the mean, right? Mean, if you want to have nerdy stat trivia tucked inside your brain somewhere, refer to the mean as the first population moment. Mean obviously is the average, right? Sum of scores divided by the number of scores. Our population mean is just the sum of all our values in a population divided by how many people there are in the population. Sample mean, sum of all the scores in our sample divided by the number of people in our sample. Pretty easy, pretty straightforward. I'm probably not the first to tell you about the mean. I'm sure you guys have a handle on that. Weighted mean is a little bit different. Weighted mean, you calculate this to find the average, the total average of two samples, okay? Weighted mean is going to be the sum of values in X, or in the sample 1, plus the sum of all values in sample 2 over N1 plus N2. Important to recognize that your weighted mean is not the average of the two sample means, right? So we have sample 1 and sample 2, right? I can't take the mean of sample 1, mean of sample 2, and add those two values, divide them by 2, and that's my weighted mean, right? We have to go through and account for number of people in this sample, number of people in that sample, okay? Except when does the weighted mean equal the average of the two means?
If your group is split half and half.
Yeah, if I got equal people in both sample, right? This starts to become important. We start thinking about this when we are talking about calculating variance for some statistical tests. If I have between subjects t-tests, we often use a pooled variance estimate because we have to say, well, I got 50 people in this group and 40 people in this group. Well, more people are contributing to variability in this group than that, and so we have to take that into account. But if we're working at paired sample tests, right, where it's just the same group of people that we measure on 2 or more occasions, then it's just the same people, right? And so then we can take some shortcuts and things. But remember that if I'm saying, oh, I want to take a look at the average of the sample in this paper or in this study, and the sample of and the average of people in this study, you have to use a weighted mean. You can't just average the two means there. Okay. Questions on that? Cool. All right. Characteristics of the mean. Every score in the distribution contributes to the mean. If I change a score, it's going to change the mean, right? Even if I've got 1,000 people in my sample, all right, change one of those scores. If I carry that decimal out far enough, it's going to change the mean. Also, if I add a new score, it's going to change the mean. Okay. What's the only circumstance where I can add a score and it doesn't change the mean?
If it is the mean.
If it is the mean, right? If the mean of my sample is 10 and I add a score that's 10, it doesn't change the mean, right? But depending on what we're measuring, that's probably going to be a rare occasion, right? So in general, when we're thinking about impact on the mean, if I add or change any score in that distribution, it's going to shift that mean, maybe by a little, maybe by a lot. That depends on how many people in the sample and how extreme the score is. If I take a constant, some constant number, I add, subtract, multiply, or divide every score in the distribution by that constant, it's going to change the sample mean by that value. Okay? And this starts to become relevant because this is something we do a lot in terms of scaling, right? So here I've measured height in inches, right? This is my distribution of height as I've measured in inches, right? But what I want to do is I want to communicate this stuff, and if I say someone's 60 inches tall, who immediately sort of knows exactly how tall that is? A little bit, right? But it takes you a hot minute to go through, okay, 60, that's, right? Probably if I just talk about feet, that's easier in terms of how we're talking about people in terms of height, right? So I might say, what I'm going to do is I'm going to take my scale here in inches and divide every value in that sample by 12, and I'm going to convert this into feet, okay? So what if I, so if I go through and say the mean here is 48, and I divide every value in that sample by 12, right? What's my new mean? 4, right? Because I've gone through and so I've divided by a constant of 12, and so I can take the mean of my original distribution, divide that mean by my constant, that's going to give me my new mean of that sample. Okay? Thing to remember, addition, subtraction, multiplication, division of every score in our distribution doesn't change the overall shape, right? If I'm just adding, subtracting, dividing, or multiplying by a constant, the distribution stays the same. It doesn't change anything, okay? The shape of the distribution here is in inches is the same as the distribution in feet. No impact at all. Okay? Now, if we start using nonlinear functions, then we start to get transforms that we use to change the shape of the data. But if all we're doing is adding, subtracting, multiplying, dividing every score in the distribution by that constant, shape stays the same. Okay. Questions on this? All right. Cool. So that's our mean. We also can select a median as our measure of central tendency. Median, as you're probably aware, is the middle score. Okay, median is our middle score. Median is the score that divides our sample in so that 50% of our scores are above it, 50% of our scores are below it. Okay, so exactly, if we split something at the median, half of our people in our sample fall above, half of our people then fall below. What we would do with an odd number of observations, we would line up, list our scores from highest to lowest, and choose our middle score, right? So if I've got 7 people in my sample, I line up all their scores, and I've got 3 scores below, 3 scores above. Median is going to be that middle score, okay? With an even sample, do the same thing, list things up, select the middle pair, and then choose the median as the midpoint of these values, right? So here, if I added another 1 onto this, right, my midpoint would be a 2 and a 3, and my median would be 2.5. Okay? So again, with an even number of scores, your median might not be an observed score. But if my scores were 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 5, 6, 7, then sort of it would still be 2. Right, because you're taking the middle pair is going to be 2, and sort of the midpoint between 2 and 2 is 2, right? So just going through and calculating your median there. Questions on median? Okay. Last measure of central tendency is going to be our mode, category with greatest frequency. Nice thing about your mode is you can use this with any scale, right? Any level of measurement, mode is an acceptable measure of central tendency to report, okay? And what's nice is if I have, let's say I need to find a measure of central tendency for ethnicity, right? Well, can I calculate mean? That doesn't make sense. Can I calculate a median? That doesn't make sense either, because it would mean I would have to rank everybody based on their ethnicity from lowest to highest, but we're working with a nominal scale, and so there isn't a lowest or highest. And so mode starts to be our best measure, our most reflective measure here, right? So advantages of mode. Now we can have distributions that have multiple modes, right? Here we have 2 modes, bimodal, here multimodal. You know, in this situation with trimodal distribution, our mean probably is a nice measure because the mean is also one of our modes, right? Here we can calculate, we can say, oh, our middle score is this, but that's actually not a frequent score that ends up occurring in our distribution, and so we start to question on whether or not a mean is a good measure of central tendency with this distribution, right? We could say we have a bimodal distribution with a mode here and a mode here. Okay? With multiple relative modes, we can have major modes and minor modes. Technically, in this distribution here, 4 is my mode because it's the most frequent occurring value that I have, right? But we got a lot of people at 0, right? So what I might report is a major mode at 4 with a minor mode at 0, and I could report that, right? And again, this is where providing some sort of graphical representation of your data can be helpful, because if you just tell me, so we have a distribution with a range of 10, and it looks to be bimodal with a major mode at 4 and a minor mode at 0. I've kind of got an idea of what that might look like, but if you just drop that in there, perfect. And I know exactly what that distribution looks like. I've got a much better idea of how these scores are playing out. Or did you have a question?
Yeah, I was just wondering how you would determine like what minor modes would be important for reporting. Like in that data, it's pretty obvious, but if you had a graph that was a little more, like would 4 be a cutoff? How would you rationalize a cutoff for a minor mode?
And this is where your expertise in your field of study starts to come into play, right? Thinking about what are we doing, what makes sense, right? So I've got a couple of different, does that make sense based on my data, right? So let's say, and again, apologize for experimental folks because we're using a lot of clinical examples, but let's say that I am looking at post-treatment scores after I treat people for depression, right? And I have a bimodal distribution there, right? What should I probably hypothesize is going on if I have a bimodal distribution in my post-treatment scores? Any ideas? Yeah.
I'd say like some people are responding really well and some aren't.
Probably, right? And this happens a lot. Some people got better, some people didn't, right? And if we've got kind of clear groups of people who this worked for and people who it didn't, I might have a bimodal distribution where I have people who are not doing so good and people who maybe are doing much better, right? So this might be where I go through and think about, okay, what did I do? What does this mean? And then how does that impact? So what's the most important information to communicate and probably use to support whatever conclusions I draw from this study, right? So if I'm wanting to point at the variability of my treatment, say, yeah, this looked like it worked really well for some people, but not for others, then I might say, as seen the distribution of scores, we have a bimodal distribution with a major mode at 10 and a minor mode at 50, right? And so starting to use this flexibly. Again, hopefully by the time this year ends, I'll have ground out rules of thumb to you and sort of just general, like, this is the things that we follow to go through. This makes, all of this is couched within your understanding of your area of study, what makes sense, and using these techniques to go through and sort of best communicate things to other people, readers, colleagues, things along those lines, committee members. Right. Other questions on this? All right, cool. So choosing an index, right? So here's our data. We've got three different options that we've talked about. How do I go through and choose? In most cases, your mean is going to be your best bet. Okay. This is because, again, with sufficiently large samples, your mean is generally going to provide a pretty representative score for everyone in your sample. Again, that's our goal, right? We can't just give you all the scores in our sample. I got to give you one score that kind of best typifies what's going on in the sample. Your mean is generally going to be your best bet. All available information is going in to calculate that mean value, which is different than the median, right? Median is just a middle score, right? It doesn't matter. You could have people scattered out to 1 billion and negative 1 billion with anything else going in between. You're just looking at a middle score, right? So, not so with the mean. Every actual value for every person in your sample gets counted in. Mean tends to have greater stability. Okay, your middle score can jump around quite a bit, but your mean from sample to sample actually tends to be quite a bit more stable, particularly with reasonable sized samples. And our mean is going to serve as a basis for most of our inferential statistics. Right? Anybody ever heard like regression or something like that talked about, referred to as means-based analyses? Yeah, that's why, because mean is central in calculating measures of variability, covariance that goes into calculating running your regression models. And so if we're talking about most of our inferential statistics, these are mean-based statistics. And so when we can use the mean, it's nice, right? But the limitations of our mean, obviously, this can be influenced by extreme scores. This happens less for clinical folks, because most of our stuff, right, is Likert type scales, or I give you a measure. If I give you a BDI, you can't score 1 billion on it, right? If I give you a Big 5 inventory, you can't have a score of 400, right? There's a limit on how high you can score with things like that. But if I'm working with income, right, or something along those lines, you can get way far out there, right? And so these are the types of things that can really start to impact. We'll go through and talk about identifying extreme values and things along those lines, but in psychological science, it typically has the practical impact of outliers are generally not as much as if we're working in econ, marketing, sociology types of things. Okay? Our mean value might not actually exist as an observed score, right? We say this is the mean. My mean is 47.6, but no one actually scored a 47.6. So I say it's the most representative value, but ironically, no one actually has that value, right? So we get a little loose there. And then also, and this is important when I'm asking you guys to think about levels of measurement, interpretation of the mean, literal interpretation of the mean relies on an assumption of interval data, okay? If I'm going to give the mean a true interpretation, it means that on whatever I'm measuring, whatever I'm measuring can be theoretically chopped up into infinitely small pieces and components, right? So if I'm measuring mass or height, mean is perfect, right? Because average height of 58.23 inches, that's an actual height, that's a real number, right? But if I'm asking you, and I'm taking the average of number of children people have, or number of rooms in a house, right? These aren't actual real values that whatever we're looking at can take on, right? And so this starts to become more problematic as we get into more theoretical types of statistics. Questions on choosing our mean? When do we choose mean? All right. Medians, right? Sometimes we're going to have data where median is going to serve as our best bet. Primarily when we're thinking about medians, we're talking about if we have data that's skewed or has meaningful but extreme values. Okay, income is one of these big things. You see income is reported in medians. Home prices often reported in medians, right? Because if I'm looking at income, the person who's making 30 million a year, that's a real value and part of the sample that I'm interested in, right? But that third person with 30 million is going to be dragging my mean out, right? And so I'm going to go through and report a median. Or if anybody do like reaction time stuff? If anybody's ever done reaction time, or if you ever look at research that's looking at reaction time, you often see fairly skewed data there, right? Because for the most part, people respond pretty fast, but then you'll have people who delay out, and so you typically have a skewed distribution, right? You can't get negative reaction time. You can get really fast, but then the only other way for that data to go is up, right? And so we might, with this skew data, we might go through and report a median value there, okay? So if we have a positive skew, right, we've got a tail going out to the right, negative skew out to the left, distribution like this, our median or our middle value might be our best choice for this distribution. Same thing here, okay? Here, we've got a value out here, but this person out here is really gonna pull that, that mean out, right? And if I've decided that this is a value that I'm interested in, right? This person is way outside the bounds of these other folks, but this is actually an important thing to capture, right? This often happens in clinical research, right? Like we go through and find that I'm doing a study of depression, and all my outliers are people with depression. I don't want to throw them out because they're the people I'm actually interested in, right? But we might not want to use a mean because that's going to start dragging us all over the place. So in a case like this, maybe our median value is going to be a better bet. Other time too when medians can become useful is if we're looking at censored data, okay? If I'm measuring miles, right, and I didn't actually measure miles a day driven, I just asked people, you know, is it, you know, 0 to 10, 10 to 20, 20 to 30, 30, 40, 40, 50, 50, 60, blah, blah, and then over 100, right? Well, I technically can't calculate a mean on that because those are as people in bins and categories, and then we've got this censored data where it's 100 and above. I really can't calculate a mean from that. I mean, if I've coded those groups 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I can calculate a mean of that, but that really doesn't mean anything, right? Because I'm averaging numbers in a sort of an ordered sequence, right? But what I could do is I could calculate the median value, right? And say median miles driven is somewhere between 20 and 30 miles a day, right? I don't need to know how many people are above sort of what the actual mileage is. I can just say, well, there were 3 people who reported driving over 100 miles a day, so that's 3 in, and then just keeping counting in toward the middle until I get to that median value. So if we've got censored data, we're often working with median values here. People kind of see what we're talking about, why median is preferable if we're working with censored data? Okay. So again here, right? I know how many people are registering each one of these. I can't calculate a mean, a true mean. I mean, I can run a number and call it a mean. That doesn't actually mean anything in terms of interpretive value, right? I can't attach something to this. But what I can do is I can calculate a median of this distribution and say, well, so the median value is somewhere between 30 and 39 miles driven a day. And technically, if we're talking about data using ordinal scales, median is going to be our preferred measure of central tendency. Okay, if we're getting technical with things, right? I have my people reporting on my Likert, my 0 to 10 Likert scale on your general overall life satisfaction, right? Well, I'm generally going to assume that people who are reporting 2s are less satisfied with their life than people reporting 7s. And even though we might use this as a continuous, and treat this as continuous data, it's really not, right? Because you have to report even numbers, and so you can't say, oh, I choose 5.5 as my level of life satisfaction, right? And I don't know that the difference between someone who's reporting 2 and someone who's reporting 4 is the same as people reporting 4 and 6, right? Because it's a semi-arbitrary scale. At best, our Likert scales are ordered categorical, and technically what we should be using for those data is a median. Because I can say this is the median value people reported, but if I say the average score, reported life satisfaction is 6.7, I mean, we do it all the time. But if we're being technically correct, that's not actually a value that someone can have, and that's not actual continuous data. And so a median would technically be better here, median doesn't depend or assume equal intervals between values, whereas implicitly a mean does, right? So again, something to think carefully as you think about how to describe your data. Questions about situations where we might choose a median as our measure of central tendency over a mean. Okay. Other thing that happens is if we're running transform data, right? We want to run a parametric analysis. So I want to run a t-test on between my two groups, but I'm looking at something like reaction time, and my data is horribly skewed, right? I've violated certain assumptions and my samples are small. So what I'm going to do is I'm going to go transform those data, right? Well, as soon as we go through and transform those data, technically what we're working on is looking at differences in median values and not mean values, okay? So if we log transform, if we exponential transform, if we square root transform our data to change the shape, technically what we've shifted over, now we're looking at differences in medians and not means, okay? So these types of nonlinear transforms, these will change the shape of the data, but not the order of scores, okay? If I'm the second lowest person in the sample, but the sample's horribly skewed, if we transform that data to change the shape, I'm still the second lowest, I'm still the person with the second lowest value in that transform data. My position didn't change around, even though the shape of the distribution did. And so what we know is the cases at the median of our untransformed variable are still cases at the median of the transformed variable. So let's say this is, okay, so if you're giving people an audit, right? So this is an alcohol use disorder. What does audit stand for? You know?
I can't remember what it stands for.
All right. Do you have, what is it?
Alcohol use disorders identification test.
Okay, good, right? So, I think we worked hard for that, for the acronym there, but whatever. Basically, you got a problem with drinking, right? All right. And so what we go through and measure people's scores. And so most people are down here at the end, and then we've got things going out. But because we're actually interested in people's drinking use, I'm not going to throw people out because they're an outlier. Because these are the people I'm interested in, right? So what I might do is I might decide to transform. And so I natural log transform these scores. So every score in the distribution, I take the natural log of every score in the distribution to get my log transformed audit score, okay? Now, if I go through and I say in this distribution, the median of this distribution is a value of 3, okay? That means if we line up everybody's score and choose the middle score, it's a score of 3. Okay, someone who's got a calculator on them. Angeline grabbed it reflexively. Right. Evelina. Sorry about that. Evelina, tell me what the natural log of 3 is. Okay. Try it again. Natural log of 3.
Can I open my calculator?
What's that?
1.098.
1.098. Okay. Sorry to put you on the spot. We don't often find the log transform on our or the natural log in our calculators, but it's 1.098, 1.1, right? If we go out and we calculate the median of our transform variable, our median is 1.1, right? So the median, the person, if I'm in the center of the distribution, if I'm at the median of this distribution, me, I have a score of 3, right? And we go through and we log transform this distribution, I'm still going to be at the median in the transform distribution. So my position relative to other people doesn't change. Everybody's still in the same order. It just changes the shape of the actual scores to make it more amenable for our statistical tests. Okay, and so, but if now I'm looking at a t-test of this group versus another group, I'm not working with the means anymore. I'm looking at differences in means. So, again, this will start to become important when we start talking about log or different types of transforms, when we would use that, and then how that impacts how we talk about data and analysis and things along those lines. But this is one of these things, when we use transforms, technically we're starting to talk about median values and not mean values. Questions on any of this? All right, choosing the mode. Mode, we want to choose the mode if we've got nominal scales, right? If we've got true categorical data, right? Things that can't be ordered, it's only membership in a certain category. If I'm looking at the distribution of majors at the university, mode is probably going to be my best bet, right? Because I can't line up, I can't order majors at the university in some way that makes sense, probably, right? And so it just, like, I'm this major, I'm that major. Mode's going to be my best bet. Okay? Also, if I'm looking at discrete ordinal data, right? Things like number of houses, number of rooms in a house, number of children, right? These are things that, I mean, technically with a median, I could get sort of between 2 and 3, right, and catch some middle number. Modal number, right, can often be helpful, and then helping in terms of the description of our shape, right? I say here's the mean value, here's the median, this was the mode, right? In terms of just communicating to people kind of what's going on with things. Okay, so for the most part, mode's going to be what we use with nominal data in order to identify the most frequent occurrence of category. But again, things we think about and sort of differentiating between these. Okay, people clear on mode, understand when we're eyeballing mode. Cool. All right, central tendency in SPSS. Again, we're going to go analyze descriptive statistics frequencies, just as we did before. We're going to go ahead and we're going to hit a option over here in the main window that has statistics asking you what you want, and we can check mean, median, mode right here, and then hit continue. For generally, when we're looking to get the mean, when we're working through examples in class, we use a slightly different approach. Same thing, you get the mean, just go and analyze descriptive statistics, descriptives, we set frequencies. We'll cover that when we get there. This is what your output might look like, requesting mean, median, and mode. So this is caps as a PTSD interview. So this is total interview score before treatment, total interview after interview score after treatment, and at, say, 6-month follow-up. So mean, median, mode at pretest. These are all looking about the same, right? So it's looking like we have, without additional information, we might think that we're kind of have fairly normal data here, but we would need to go through and get some other stuff to make a strong conclusion about that. Mean, median, and mode are starting to look a little bit different at post. What is this starting to suggest here? Yeah, it's starting to look skewed, right? Because we've got mean out here, we've got median and mode starting to layer out here, right? And then we got all sorts of stuff going on here, right? And so looks like, you know, this is giving us some additional information about what this distribution looks like. But with this, I would probably want to look at some more types of things to get a good sense for what these data look like. Okay. So this is SPSS. In Stata, we can hit sum, which is short for summarize. So we summarize caps, state, trait, anxiety, inventory, and then hit add on this detail. And this is going to give us mean here. Median is going to be our 50th percentile. That's our middle score here. So you're getting some of the same stuff in Stata. We don't get mode in this output, but we can hit M modes, race, education, marital status, and it's going to give us modal values for there. So again, just a different program, a different way to go through and request stuff. All right. How we doing?
On the SPSS, it only counts the valid responses in?
Uh,
Is it pulling everything?
yeah, no. Yeah, this is only counting because it can't count the missing because there's no,
It doesn't even pull it all?
for this variable. So this is going to be the mean, median, and mode of the 34 values that we have available to us. So it's a good question. All right. Questions on any of that? We're flying through this. We're cooking with oil today. Feeling good? All right. It's exciting times. Exciting times. Remember this for the rest of your life. Variability. Okay. If we're talking about moving away from central tendency and talking about the degree to which scores in a distribution are separated out or clustered together. Okay. So if we have all of our scores in a distribution are all the same, there's no variability, right? If there's no variability, do we have a variable? No, we have a constant, right? But we can get a distribution of scores where everything's pretty clustered together, or if we start to see large differences between individual scores, then we would identify that as having a lot of variability. Variability is a hard thing for people to kind of wrap their head around. Show of hands, be honest, like when you were first exposed to this idea of variance, standard deviation, people have a hard time kind of wrapping their head around what that means, yeah, right? Central tendency is easy, right? Yeah, that's the middle score, I got that. Variability can start to become hard, but this is arguably a far more important concept than kind of your middle scores here, okay? So this is something I'm gonna beat you over the head over and over and over and over. You'll get at it by the time we finish up. If we're talking about variability, there are a lot different metrics of variability. Typically what we're doing is we're qualifying a distribution in terms of distance. How far away are scores from one another? Measures of variability should generally tell us how much of a difference to expect from any two randomly selected scores or from any score from the mean if we're talking about standard deviation or variance, okay? It's telling us if I were to sort of close my eyes, pick a score, two scores out of the hat, how far would I expect them to be from one another, right? And so we've got different metrics that start to speak to or give us some idea of how much differences we see in between scores in a distribution, okay? If we think about our measure of central tendency, let's say the mean, right, as our most representative score, right? Our measure of variability tells us how well we should expect that individual score to represent the distribution as a whole, okay? So if I have, let's say, I'm measuring mass, okay, and I say average weight in people in my sample in pounds is 150 pounds, okay? Say, okay, well that's kind of the best represent, like if I had to guess, sort of someone's coming in through the door and they're from my sample, and I know the mean of the sample is 150, what's my best guess of person A coming through the door from that sample in terms of their weight? 150, right? Am I gonna be right with that? Probably not, but it's my best guess. I'm gonna be off by the least amount if I just guess the 150 for everybody comes through the door. But let's see, we change the game a little bit. Now I say you have to go through and place a wager on how close you are, right? And you can choose how much you want to bet, $1 up to $100, right? And I know that, say, so I tell you the average of weight of the person in the sample is 100 or 150 pounds, and the standard deviation variability is 20 pounds, okay? Are you going to bet a lot or a little in terms of how close you are if I know the variability is 20 pounds? Not very much, right? If you're going to stick a gun in my head, force me to wager on this, I'm going to drop dollars down, okay? What if I tell you that the standard deviation is 2 pounds? I'm going to jack my bet way up, right? Because with the variability, standard deviation of 2, I know that there's not a lot of, like, somehow I managed to collect people who were all right at about 150 pounds, right? But with the greater variability, people could walk through the door all sorts of ways, right? I don't know, right? And so variability, our measures of variability tell us, okay, here's our measure of central tendency. Our variability tells us how close we should expect, or how representative should we expect that measure of central tendency to be. You can also think about this as telling us how much error to expect. Okay? When we get into means-based analyses, and I say, all right, I've got condition A and condition B, right? And I'm saying that for condition A, these are people who were randomized to condition A, everybody got the exact same thing, right? And if everybody got the exact same thing, what should everybody score in that group be? If whatever our outcome is, so we are measuring some outcome, and my hypothesis is that the only thing that impacts that outcome is something that I've gone through and manipulated, okay? What should I expect everybody in that group's score to be? The same, right? It should all be the same. Because if I'm manipulating the one thing that impacts this outcome, everybody who came in and received whatever I got in that they got in that condition, everybody should have the same, right? And so I say average value is 20 for this group, right? What if people don't score 20? Well, then that's error, right? That's something that's not being accounted for in my experiment, right? And so thinking about variability is telling us how much error we have in our best estimate of this is the most representative stuff. Okay? And so this starts to be crucial. This gets at the very foundation of our inferential statistics, thinking about variability and error and predictive values and things along those lines. Just like measures of central tendency, we've got different types of metrics that speak to variability of our data set. First index we'll talk about is range. Okay, range is easy. We know what range is. We've been exposed to range. Range, the distance between the largest score and the smallest score in a distribution. Right? What are the upper and lower limits? What's the max? What's the min? Right? A couple different ways people will calculate range. You can calculate highest minus lowest. In the highest minus lowest plus 1, you'll get bent out of shape on which one's right, which one's wrong. This is what SPSS does when it calculates range. People will get sort of worked up like in introductory statistics, your undergrad statistics on sort of adding 1 to that thing. It matters 0, in fact. So just kind of know that sometimes people will calculate it differently, get bent out of shape about it. But so a very, very easy and simple measure that gets at variability in our set, but we do have some limitations, okay? Range is determined by 2 extreme values, ignores all others in the set, right? I've got a sample of 200, and to calculate my range, I'm calculating that based on 2 scores from that set of 200, right? So we're not using anywhere near all the information available to us. Can also lead to misleading inferences in distributions having unusually larger and usually small scores, right? So I've got something that looks pretty good, but then I've got an extreme score to the left, extreme score to the right. That's going to make my range be a lot bigger. If you just tell me what the range of that distribution is, I'm going to think these scores are far more spread out than they probably are in general. Okay? And then because our range doesn't consider all the scores, it's often not, we don't see range used a lot as the main index of variability for a set of data. Okay? So if we look at something like this, right? Here we've got a small set of scores, and in general, if you ask me what's going on, I would say, well, most people are right in this 3 to 7 range, right? And that's where everybody lives, right? But if we were to calculate range, we've got this person out here, and so our range is, let's say that's 20. We've got a range of 17, right? That range value doesn't represent well what's actually going on with most of these, right? Because what we've done is we've calculated this statistic using only 2 values, and basically it's suggesting a greater amount of variability in this data set than is actually present if we actually take a look at our scores. And so range is nice. Range can be useful in terms of descriptive purposes. Again, if I want to keep coming back to income, right? But income, right? This is the range of income for people in my sample. This was the lowest, this is the highest. That's a number, I sort of know what that means in terms of dollars because we use them daily, right? But probably not going to be our primary measure of variability for a set. Questions about range? Okay. Other types of range statistics. So we can start to get into more detailed deviations of range as opposed to just the highest and the smallest, the difference between the highest and the smallest. We can work with quartiles. Okay. Anybody here have experience with educational testing, intelligence testing, cognitive achievement types of standardized test things? No? Okay. If you do, and for clinical folks you will as you go through and take assessment classes and things like that, talking about quartiles, right? So if I score, I get my quartiles and percentiles. If I get my SAT back, do I want to score in the 90th percentile or the 10th percentile? 90th percentile, right? That means that I scored better than 90% of the people who took the test. If I'm in the 10th percentile, that means I scored better than 10% of the people, which means I'm sort of down there at the bottom, right? Quartiles are similar to, quartiles are the same as equivalent to percentiles at certain areas. First quartile, this defines the lowest 25% of the distribution, okay? So what we're doing, sort of like a median, we're separating all the scores out, we're putting them in order, and we're counting up till we get to a quarter of the sample, saying this is the cut point. A quarter of the sample falls below this, this point. Second quartile defines the center of the distribution. This is your median, okay? Second quartile is your 50th percentile or your exact middle score. Your third quartile, defining the upper 25% of the distribution, this is the 75th percentile. You're saying that if this is the third quartile, we're saying 75% of scores fall below this value. Okay? So breaking things up into quartiles, we have the first, the second, the third quartile, and then our interquartile range. This is equal to the difference between the first and the third quartiles. Okay? You'll hear this referred to as the middle 50. It's taking the middle 50 score, or the middle 50% of scores in your distribution. So you've got the upper 25% is cut out. You got the middle, the bottom 25% cut out. Your interquartile range is just the distance or the number of values between your third quartile and your first quartile. So if we're thinking about sort of this nice normal distribution here, we've got the lowest 25% of the distribution, here's our median, right? We've got, this is going to be our cutoff for our first quartile, our third quartile. Here's the upper 25% of the distribution. My interquartile range is cutting just this right center 50% of the distribution, cutting that out. And we're cutting off the upper 25%, lower 25%. Okay, yeah?
What happens to that 50% that you're cutting out?
What's that?
What happens to the 50% that you're cutting out?
So this would just be a range statistic, right? And so this would be, say, my interquartile range for this distribution is 20, right? And that means that we have a span of like 20 values between the first quartile and the third quartile, right? And the bulk, if we've got a normally distributed data, the bulk of, well, exactly half of scores will fall in that middle by definition, okay? And so this is, again, just to describe a different means of describing sort of the middle, the range of sort of the middle, right? Because this is kind of where the bulk of people are. And so we're going to say the middle half of our distribution, what's the upper and lower limit that captures kind of the middle half of our distribution there, okay? In certain types of we don't see this a whole lot in terms of psychological statistics, but if you get into other types of research areas, this starts to become more important. And we use this a lot when we start to talk about box plots and things along those lines. Okay. Questions about interquartile range, quartiles, kind of how we would interpret those? And so this, in like educational testing, cognitive achievement testing, starts to become important, right? Because what you get is your percentile ranking for where people are at, right? And so if I have, if I go through and I take an IQ test and I find that my IQ is 100, what percentile score is associated with my score of 100? What is it?
If it's 100, it's
It's
gonna be 50.
going to be 50th percentile. That means exactly half of people who take this exam will score below me, which means I'm right dead center, right in the middle, right? And then what we do is sort of, as we go up or down, sort of calculating different percentiles and things like that. Questions? Cool. All right. Limitations of our interquartile range. People will say, well, that's fine, but we lose a lot of our data, right? Literally, we're excluding half of our data. The upper 25%, the lower 25%. Who knows what's going on in there? We're just saying these are the bounds for the middle 50, and then so the other half of the data are hanging out there in the wings somewhere, right? So we can get criticized. Same thing if we're Windsorizing data or sort of chopping things down back. Well, that's fine, but you just kicked out a whole bunch of your data, right? And so some problems with that.
I was gonna ask, when is this particularly useful? Like in what kind of study or what kind of research question would you be asking when this would be a good idea?
We get a lot of biological data, like Zophis. So like my brother's a biologist for the state. He works for the game and fish, and then work with large predators and bears and bighorn sheep and watching kind of where they're moving around and stuff like that. Like these types of things start to become more relevant for those types of studies. I think some stuff in like econ will start sort of looking at some of this stuff. We don't use this a whole lot, but what I want you to know is I want you to be aware of it and know how to go through and interpret it, because it can be. We often don't use things very commonly, not for good reasons, when these could be very useful ways of communicating information to people. So I want you to just become familiar, be able to know how to, if you were to be confronted with a study that you're running or a dissertation or a thesis or something like that, big boy, this would actually be a nice way of you going through and communicating this to people. You've got that tool in your pocket, you can go through and use it. And for those of you who go on to take Tara's Assessment 1 class, this will start to become important when you're talking about percentiles and things along those lines, and how to sort of find people's rank or position in a larger distribution of scores and things. All right, questions? Okay, let's stop and take a break. You can go through, take 10, be back, stand up, stretch, take care of personal needs, anything you need to do, and we'll get started at 3:40. All right, folks. We'll jump in just so we can get through all this stuff, make sure we don't have any carryover into next week. But any questions about any of this up to this point? Most of this stuff review in terms of things that you've been exposed to before, sort of not a lot of new information. Nice reminder. Okay, cool. Oh, whoops, I forgot. Look at this, I'm like, oh, by this time, and then I lied to you and started before. Maybe there's an act of aggression, right? Because treating me as an outsider. I mean, like, let's start and get talk about all the good stuff before that marketing person gets back in. All right. So going through talking about variance and standard deviation. Okay. Variance, standard deviation. This measures variability that's going to come up. It's going to be most common. And wanting to get really solidified conceptually understanding what we're talking about when we're talking about standard deviation, talking about variance. Standard deviation, loosely, we'll talk about why loosely. But if you hear, standard deviation, you can generally think about this as our best estimate of the average distance of any given score from the mean, right? So if I say, here's a distribution. The mean is 50, standard deviation is 5, right? What I'm saying is, on average, if I were to go through and pick scores blindly from a hat, right? On average, those scores, I would expect those scores to be about 5 units away from the mean, on average. Now, some of those are going to be much closer to the mean. Some of those are going to be a lot farther away from the mean. But on average, if my standard deviation in this distribution is 5, it's saying, on average, The distance between any two randomly selected scores is going to be 5. The distance between a randomly selected score and the mean is going to be 5. It's just a measure of the average distance, roughly speaking, of any two randomly selected scores. Okay? And so this helps, right? Because again, in introductory statistics and undergrad statistics, we learn about standard deviation, we learn how to calculate it. But I would imagine if you're like me, not having a good sense for what does that mean practically. If you say, oh, standard deviation is 10, I'm like, okay, well, tell me what that means in a way that makes sense to me. You would probably struggle with that, right? But from a conceptual standpoint, we're saying standard deviation is on average the distance between any two randomly selected scores, or the distance of any randomly selected scores from the mean, right? And then that starts to actually, I can visualize that. I can kind of see what that means, right? Variance. Now we talk about standard deviation a lot in lower level statistics, and talk about standard deviation, all the time. Variance is actually our second population moment. Variance is what we get our standard deviation from. Mean is first population moment. Variance is your second population moment. And it's the average squared distance. So you could roughly interpret this as the average squared distance from the mean. Okay. This is less intuitive. Okay. Our variance is essential for our inferential statistics. We're going to be working a lot with variance. You hear us talking about variance all the time, but practically less interpretive value with variance. But we can move back and forth between variance and standard deviation quite easily. If we take our variance and take the square root of variance, that gives us our standard deviation. Take our standard deviation, we square it, that gives us our variance. We're just rescaling this, moving this back and forth, but making sure that we're not using these interchangeably when we start to get into things like effect size and other types of variance estimates. It's going to be important that we keep variance separate than standard deviation. Okay, and what ends up happening is we end up calculating variance standard deviation difference for population versus samples. Okay, but this is important. Okay. Think about standard deviation. We talked about standard deviation, what standard deviation is. We like standard deviation. Standard deviation is cool kid, right? We sort of excited about that. It goes through, we can get a good sense of what's going on. But as we start to sort of get deeper into the mix of this sort of stuff, your variance, that's actually where it's at. Variance is the thing that's going to be much more important for our statistical procedures. Standard deviation is a nice way to communicate stuff. But don't write off variance, because variance is going to become much more important as we go through. Variance is going to grow and bloom. You're going to come to love variance far more, and then think standard deviation is cute, but variance can be much more important for the types of things that we're doing, okay? So again, as part of this whole sequence, we want you to be very clear and have good conceptual ideas of what we're working with. And Laura, as you're going through, I hope you're writing out variance equals the rock, right? That's what I hope is on this.
I would love if I could draw it out.
All right, so we're calculating variance and standard deviation, and we're working with a population of scores. Okay, these are all the people of interest, right? This is the entire population. This is everybody, right? What we would do and say, in this example, our population is small. Our population includes 5 people, right? These are 5 genetically modified rats that are all the genetically modified rats in the universe. It's just these 5, right? And so if I wanted to calculate variance here, I have my scores, and the first thing I'm going to do is calculate a deviation score. Now, someone with a calculator at hand. Okay. Tell me what the mean of this set of scores is.
It's brand new.
What is it?
6.
Is it 6? Yes, you're right. Thank you. Sorry, I didn't mean to question you. I thought it was 4 in my head, but it wasn't. It was 6, like you said. So we've got a mean of 6, right? And so the first step that we're going to do is we're going to go through and we're going to calculate a deviation score. Deviation scores are going to become incredibly important. So if I talk about a deviation score, you know that deviation score is just going to be the score minus the mean of the sample. Okay? So if we go through and we subtract 6 from every one of these scores, we get our deviation scores here. Okay? That's step 1. Then step 2, we go through and we calculate the square of each deviation score. Okay? So we're gonna take our deviation score here, our raw score minus the mean, and then we're gonna take that to the power of 2. We're gonna square it, okay? What happens when we square these deviation scores mathematically? What do you think, John?
Takes them if they're like negative.
Yeah, it makes them all positive, right? And this is going to become important because what we need to do is we're going to go through in step 3 and we're going to add these squared deviation scores. When we add our squared deviation scores, this gives us the sum of squares, right? Again, sum of squares, again, one of those statistical terms that seems frightening, and we know it's a thing, but if you asked us what it was, I don't know, right? Very literally, a sum of squares is just the sum of squared deviation scores, okay? So if we take these, we square them, we get our column of squared scores, we add these up, this gives us our sum of squares. What would happen if we tried to if we just tried to add up our deviation scores, Amanda?
You times 2.
Well,
Well, you have negatives, so.
yeah, so what do I get if I add up this column? 0, right? Is there ever going to be a circumstance, if I've calculated things right, where I can sum up my deviation scores and not get 0? Nope. Mathematically, by definition, if you add your deviation scores, you'll always get 0. That's not useful, right? But what we can do is we can go through and square those deviation scores and then add those up, and this gives us our sum of squares, right? Our sum of squares is just like variability or standard deviation. It's just a raw metric of how much variability we have in these data. Now, sum of squares are important computationally, but even less useful in terms of interpretive value. I can tell you I've got a sum of squares of 800. Is that a lot of variability or not a lot of variability? Who the hell knows, right? Because I can't actually make an interpretation of that. But if someone were to ask you, well, what does sum of squares mean? That just is just literally the sum of the squared deviations for this population, this sample. Okay, so we add those up, and then step 4, we're going to divide our sum of squares by the number of scores in our population to get our population variance. So we take our sum of squares divided by the sample. So we got 40. We divide it by 5. This is going to give us our variance. Okay, population variance indicated by sigma squared here. And then we're going to take the square root of our variance to calculate the population standard deviation, take that, and then we get that. Okay. People kind of see sort of conceptually kind of how we're walking through and calculating both our sum of squares, our variance, and our standard deviation. Okay. So this is the conceptual sort of walkthrough of how we do it, but this can actually be, this would be a lot of columns to lay out, particularly if you have more than 5 scores, right? So computational formula for calculating your population sum of squares is going to be the sum of your squared x values. So if you take these x values, square these, add them up, minus the sum of the square of your sum of your x values over n. These two things are equivalent. This is just easier to calculate than sort of, think about this. Your computation formula is a shortcut, okay? So it keeps you from having to calculate individual deviation scores for everybody in there. If you do it this way, or if you do it this way with the set of scores, you're going to get the exact same number there. Okay. Questions on how we're walking through calculating population variance, population standard deviation? All right. So, and I can't express to you how important this is for everything that you do. Anytime you calculate any type of statistic, right, whether it's for this class, for your own research, you should always ask yourself, once you have that number in hand, ask yourself if this makes sense. Does this number make sense given what I know about things? Okay, so let's say here we've got a set of scores and I have a mean of 6. Okay? And I know that the distance between my mean and the next closest value is 1 and the farthest value is 5. What should my standard deviation, where should my standard deviation for this set fall? do you think, Nick? This is a problem set, this is problem 3, and I go through and I calculate, I got a standard deviation of 7. Does that make sense? Why not?
Because your furthest value is only 5 up.
Yeah, right? As far as I could get, right? So if I'm thinking about the standard deviation is the average value of any randomly selected score from distance from the mean, that doesn't make any sense, right? And so plausibility checks always important, right? And this is why it's so important to know what it is you're calculating, why, how you calculated it, because that's when you go through and you get, I calculated a correlation of 3. Does that make sense? Nope, right? Because you can't have a correlation of 3, right? I calculated a variance estimate that's negative. Can that happen? Nope, right? Knowing what's going on and how to go through and check is always important, okay? Again, going back to this Wilkinson article, so we're getting side-eye right here, right? No substitute for common sense. Never assuming using a highly regarded program absolves your responsibility of determining whether your results are plausible, right? People love online calculator. I'm going to throw this into an online calculator. I got a effect size of 300, right? So I'm just going to report that. That doesn't make any sense. Either you screwed something up or whoever put together the online calculator doesn't know what they're doing, right? It's up to you to go through and say, does this make sense given what I know about these data, okay? And this is where when we get into stuff, it's going to help for you to literally, what does this mean? Literally, what is the interpretation of this statistic? That's going to help you say, is this reasonable? Is this not reasonable? You're going to be doing yourself a ton of favors here. All right, questions about how we might plausibly check whether or not our standard deviation estimate's reasonable? Okay. So that's fine. If we want to calculate variance in a population, but is this useful? No. When are we actually working with populations? Never, right? If we have populations, do we need inferential statistics? Nope. Do we have population values? I don't need to say is there a statistically significant difference between population mean here and population mean there? Well, I don't. Yeah, it's whatever the difference is, because I've captured all scores. This is the actual literal difference. I don't need to bring inferential statistics into it. But we're never working with populations, right? We're working with samples. And so when we're working with samples in our goal of inferential statistics, what we're trying to do is draw conclusions about our population, right? Remember, we're cold, callous, heartless people. We don't care about our sample. I care zero for you, sample. You're a means to an end. The only reason I care about you is to get at this larger objective of learning something about the population. I don't care what your characteristics are at all, only insofar as you're representative of this population that I'm much more interested in. We're using our samples callously. It's not ethical maybe, but that's what we're doing here, okay? And so we're assuming that our samples are representative, and we're very, very much interested in characteristics of the sample, or excuse me, characteristics of the population, not characteristics of the sample, okay? But what ends up happening when we're calculating variance is we have a problem, okay? Samples consistently underestimate population variability, okay? And it's because extreme scores, right, are sort of farthest most in a population, and let's say we're thinking about height, right? And I want to look at sort of average human height, right? And so I go through and I capture 100 of people, 100, and let's say it's even representative, right? Let's say I somehow manage to get a representative sample of height of 100 people from the US, okay? Adults, 18 to 90, right? And I literally get a nationally representative sample of height with 100 people, okay? I'm going to get a range of scores, but I'm probably not, am I going to, in that sample of 100, am I going to capture the tallest adult in the nation? Probably not. Am I going to capture the shortest person in the nation? Probably not. And so what ends up happening with our samples, if we're looking at variability, we're systematically excluding, we're missing those extreme values, right? And these are values that are real values in the population, right? But what ends up happening if we look at the population variability just in terms of range, right? This is the variability of the population, right? But just based on, like, this is where most people exist, when I get samples, particularly if they're small samples, where are my samples probably coming? from the center, right? We're probably getting them right from the center because that's where most of the people are. This is where we're most likely to draw people from. And so right down in the center, and so this is our sample variability, right? And so we say, okay, well, we didn't capture the tallest person and the shortest person in the nation. So we run another sample of 100. Do we catch the tallest and shortest person? Nope. We do it again, and we do it again, and we do it again, and we do it again. Eventually, we'll probably capture the tallest and the shortest person. We're probably not in the same sample, and it may take us 100,000 tries before we get one or the other, right? And so sample after sample after sample is still coming in generally from here. We might pick up people in the tails, but what ends up happening is if we go through and we calculate the variance of our population, if we're trying to estimate the variance of our population based on our samples, our statistic is biased, right? Because our statistic is systematically underestimating the variability in the population. Okay. People see kind of what the problem is with variance as a statistic we just calculated for the population. So if we're thinking about bias and unbiased statistics, we would say that a sample statistic is biased if the average value systematically overestimates or underestimates corresponding population parameter. This gives us a biased statistic. Okay? Sample statistic unbiased if the average value of the statistic is equal to the population parameter. So here, if we go through with samples of 100 and we collect 100,000 samples, right, and take the average of those 100,000 samples, right, and we take the average variance that we get from those 100,000 samples is still going to probably systematically lower than the actual variance in the population. So we have a biased statistic. Okay. Now, is our mean biased? Mean's not biased, right? Because we're going through with each one of these, we're kind of capturing people in the middle, and so we might capture people at the big and the small end of the distribution. But our mean is an unbiased statistic. We don't have to change how we calculate mean. Mean is an unbiased statistic. But if we're using the population formula with our samples to estimate the population variance, what we're going to get is a statistic that's, on average, systematically smaller than the actual value that we're working for. And so we would see that, we would say that if we're using our population formula for variance in our samples, we're going to produce a biased statistic. Okay. People kind of see what's going on here and what the problem is. Good news is the bias in this estimate is consistent, and we can fix that real easily with a slight modification to our formula. Okay. So what we do with the population, if we're calculating population variance, remember we calculate our sums of squares, and then we just divide it by the number of people in our population, or the number to correct for that bias, is we divide our sums of squares by the number of people in our sample minus 1. Okay. And so, Haley, tell me what happens to my variance estimate if I divide my sum of squares by n, either the number of people in my sample, or n minus 1. What does that do to my output?
I'm not sure.
Okay, let's say, so my sum of squares is, what's my sum of squares? Just give me a number.
40.
40, okay. And let's say I've got 10 people in my sample, right? And so I take 40 divided by 10, what do I get? 4. What if I get 40 divided by 9? Is that going to be a larger or smaller than 4? Larger, right? This is an important thing. A lot of the stuff that we're going to be working with this year has to do with these ratios, right? Think about it. If I've got a number and I divide that number by a bigger number or smaller number, what happens if my divisor gets smaller and smaller and smaller? What happens to my outcome? What happens to it? What does it do? It's bigger and bigger and bigger, right? If I take this denominator, this divisor, and I make it larger and larger and larger, what happens to my output? Smaller and smaller, right? Sort of a lot of the stuff that we're working with is all based on ratios, right? And so when we get into t-tests and inferential statistics, a lot of times our standard error is going to be what's going on in the denominator. As our standard error gets bigger, right, as our measurements get messier and messier, what happens to my test statistic is I'm dividing sort of this by a number that's bigger and bigger, what happens to my test statistic? It goes down, right? And if I want a big test statistic, that's problematic, right? Because I get better and better at measuring my stuff, and I get that standard error tighter and tighter and tighter. I get bigger samples, I get better measurements. That standard error gets smaller. What happens to my outcome? It gets bigger, right? And so this is an important concept. It's going to be relevant to effect sizes. It's going to be relevant to our test statistics. So this basic understanding, if I divide things by smaller things, my output gets bigger. If I divide things by bigger things, my output gets smaller. It's kind of a fundamental thing that's going to keep coming up again and again, right? So my problem is, if I use my population formula on my sample to estimate population variance, I'm generally only getting in the middle of it, and so my estimate for variance is it's systematically smaller than the population estimate. But if I go through and make a small adjustment, and I divide my sum of squares by a smaller number, not n, but I divide it by n minus 1, okay, what does that do to my variance estimate? It makes it larger, and so it corrects, right? And what am I going to, and so let's say what am I going to, and so okay, I'll quit picking on you, someone else, right? Where am I going to get the bigger correction? With a smaller sample or a larger sample? What do you think, Kate?
Oh wait, no, what?
Yeah, no, I forgot what direction I asked the question in. So, correct, yes.
Okay.
So I'm going to get bigger adjustment with a smaller sample, right?
Yeah.
Because if I'm looking at the difference of dividing a number by 10 versus 9, that's going to be a much bigger change than if I'm going from 500 divided by 500 versus 499, right? And so this starts to make sense, because if we go back through and take a look at this, which one of my samples is going to be more representative? If I have a sample of 10 in terms of capturing people's height, or a sample of 500? 500, right? With a sample of 500, I'm going to have a much better chance of catching those extreme values. And so the adjustment that I need to make that sample unbiased is going to be much smaller than if I'm working with samples of 10. Samples of 10, I'm going to get right in the middle here, and I'm going to seriously underestimate population variance with samples of 10. Still going to be systematically underestimate with samples of 500, but my bias is going to be much smaller with the larger sample than the smaller sample. Okay, so people kind of start to see what we're doing with this correction and how it's adaptive depending on the size of our sample. Okay, your sum of squares is also going to get bigger with the size of your sample, because remember, that's just the sum of the square deviations. So I've got 500 people in my sample. That's a lot of numbers to add up. I've only got 10 people. It's only 10 people to add up, right? And so this goes through dividing by n minus 1 as opposed to n. This is going to reduce the number, or reduce the denominator, resulting in a larger estimate that's going to account for the fact that we're using sample and not actually calculating out of the population. Yeah?
This might be a bad question, I haven't decided yet.
No, it's probably an excellent question.
Okay, so it says the sample statistic could be biased to over or underestimate the population parameter.
Mm-hmm.
If it's overestimating it, would it not be problematic that we do the n minus 1?
But it's not, okay. This is just talking about certain types of statistics. If you hear a statistic as bias, right, that means that this statistic, as it's calculated, systematically overestimates or underestimates the population parameter. The problem with calculating variance and estimating population variance using sample data with a population formula, that's always going to underestimate. So we're always concerned with variance. Our sample variance is never going to systematically overestimate population variance. It's always going to underestimate it, and so this is the correction we have for that. So if we go through and we think about calculating variance and standard deviation for a sample, again, we've got our column of scores, and now instead of having a population of 5 individuals, this is just our sample of 5 individuals, right? Same thing. Step 1, we're going to calculate our deviation score. Step 2, we're going to square our deviation score. Step 3, we're going to sum our squared deviation scores to get our sum of squares. Have we done anything different yet? Nope. Population formula, sample formula identical in terms of our calculation of our sum of squares didn't change at all. But then what we're going to do to get our variance is we're going to take our sum of squares and we're going to divide it by the number of scores in the sample minus 1 to get our sample variance, okay? And so in this case, instead of dividing 40 by 5, we're dividing 40 by 4, which is going to end up giving us a larger estimate relative to if we would have used the population formula. And then to get our our estimate of the population standard deviation using the sample, we're just going to take our sample variance, take the square root of that. That's our sample standard deviation, right? And again, what this is all doing is it's going through and it's correcting for this systematic known bias that we have when we try and estimate our population variance using a sample. We have to make a small correction there, okay? And again, computational formula for sum of squares is identical because we didn't do anything. We didn't change anything with calculation of the sum of squares. Where we get our correction in is what we use as our divisor in that formula. So, population versus sample variability. Sum of squares, in that last example, 40 for each, right? Doesn't matter, we don't screw around with changing how we're calculating some of our square deviation scores. But we are going to get a difference when we calculate variance, right? If let's say that I have a sample of 5, but I use a population formula to calculate my variance, I'm going to get 8. Versus if I calculate it using my sample formula, I'm going to get 10, right? So we get a bigger number. I'm assuming that if I use the population formula on a sample, it's going to underestimate the population variability. I need to adjust it, right? And we can see we have a 2-point adjustment in variability. That's actually pretty big. But again, our sample was very small, so we get a big adjustment. Standard deviation, we take the square root of 8 here, square root of 10 here, gives us our standard deviation. Again, thinking about our standard deviation estimate is, on average, the difference of any randomly selected score from the mean or the average distance between any two randomly selected scores, giving us a sense and sort of something we can think about in terms of how spread out or clustered together these scores are. Okay. And so population formula, sample formula. Only going to use population formula unless I tell you use a population formula. In applied stuff, you're probably never going to use this. Always going to use this because we're always using samples whenever we're working with populations. Okay. Questions on all of this?
This might be more construct than this, but like kind of building off what she said, what if you sampled kind of a weird talkative for height, maybe malnutrition people, and it was relatively small compared to the average height across the rest of the region or across the rest of the US. Is that, how does that affect your data?
That's a design issue.
Okay.
Okay, and that's not something we can correct with magical numbers,
okay.
right? Now, sometimes you might just happen to capture all of the malnourished individuals and find that they're far shorter or something like that. But hopefully, based on your understanding of how tall people should be, and as you're collecting your data, something should get flagged somewhere in there and saying, oh wow, I kind of maybe got a problem. Okay. Probably more generally what's going to happen is you've decided to conduct a study and your convenient sample happens to be people who may be disadvantaged and suffer from malnourishment and things like that, and now you've got kind of a different situation on your hands. Okay. But that type of thing is a methods issue that we can't fix with this. There's no correction for bad sample, right? There's not a constant that we can add or divide that accounts for your cruddy methodology, right? So, but that's the type of thing that starts to come in and we want to think about in terms of your interpretations. Other questions? All right. Utility of our standard deviation. Again, we're describing variability in terms of typical distance from the mean or typical distance between any two randomly selected scores. For any distribution, we're going to have some individuals that are going to be close to the mean, other people are going to be much farther away from the mean. Our standard deviation is just telling us, on average, how much distance we should expect. If we know both the mean and the standard deviation, what we can do is it tells us information about the general distribution of our scores, how spread out are things, tells us where, if I were to select a grab a randomly selected score, where that score should occur or where it should fall, and we can start to tell much more about individual scores relative to their position in the overall distribution. Okay? So if we're thinking about a normal distribution of scores, and this is probably familiar. We see that for scores falling generally on a normal curve, we find that about a little over 2/3 of scores are going to fall within a standard deviation above or below the mean. Okay, this is about, so if we're thinking about our our middle 50%, this is getting a standard deviation above, a standard deviation below. Going outside that, getting about 2/3 of your sample in a normal distribution is going to fall about a standard deviation above or below. Think about this in terms of intelligence testing, right? IQ tests have a mean of 100, standard deviation of 15, right? So about 2/3 of the population are expected to fall somewhere between a score of 115 and 85 in terms of this, right? As we start to get more standard deviations out, right, we start to get less and less likely scores. So if we go 2 standard deviations above and below, right, that captures about 95% of our population, almost everybody. 3 standard deviations out, over 99%, right? And so what happens if I find a score, Layla, that's 3.5 standard deviations from the mean? Is that a likely score if we're assuming a normal distribution? Nope, that's pretty rare, right? That's, I've got someone of an IQ of over 150, right? Like that's an unlikely score, right? That's probably not going to happen very often. That's way off in the tail, right? And so what we can do, and we're going to go through and start using, this is particularly important, we start using effect sizes and using standard deviation units as our general unit of standardization. We can start to make inferences. If I know a mean and a standard deviation of a distribution, I can start to give you and tell you whether a score is, how extreme a score is, or how likely we are to have pulled the score, given score by chance. So let's say if we say average height of adult males is 5'10" with a standard deviation of 3. Okay. So we're saying on average from adult men, if I just randomly select someone's height, they're probably going to be about 3 feet above, or 3 inches above, or 3 inches below 5'10", right? So I randomly select David, right? And David has a height of 5'6". Kate, is that, what can I infer about David's height relative to the population more generally?
It's not extreme.
It's not extreme. How do you determine whether that it's not extreme?
Because you can just look at the mean and then, so I just subtracted the 3 from there to see if that score falls close to it.
Okay. So if I go standard deviation below, I've got 5'7", right? So David's falling a little above the standard deviation below the mean, right? So is David tall or short? Shorter, right? So you might notice that David's noticeably short, but he's not terribly extreme, right? What about John? John's 6'6". John, is that an extreme value or not an extreme value? What do we say about John?
Would be an extreme value.
Yeah, I mean, he's getting close to 3 standard deviations above the mean, right? And if we think about where that distribution falls, that's pretty high, right? Matthew's 5'2". What do we say, Matt, about Matt?
He's noticeably short.
Noticeably short, right? We're getting close to 3 standard deviations below the mean there, right? And so we can start to use our information about, and again, we're assuming a normal curve, but height we would expect to be on a relatively normal curve. We can start to make inferences about how extreme a certain value is, whether or not this person is typical or atypical of a population. Same thing if we look at extroversion scores, right? We have a mean of 85, standard deviation of 20. We can go through and start identifying sort of whether or not these are, we don't even have to know anything about sort of the scaling of this measure. If you give me the mean and standard deviation, assuming that extroversion falls on a relatively normal distribution, I can start telling you whether or not this is something that would be expected or not expected based on the values there. Okay. And this is a heads up, and this is starting to ring bells. This starts to get into things like Z-scores and standardized scores, and being able to, assuming a normal distribution, identify positions and probabilities of randomly selecting a person at or above certain levels. Okay, we'll get into that next week. All right. Questions about interpreting and using mean standard deviations to try and generally get a sense for position of scores? Okay. Standard deviation and inferential statistics. Again, when we start to get into our inferential statistics, what we're trying to do is we're trying to detect meaningful patterns, right? I see a difference between group A and group B. Is this something that's probably something that's replicable and meaningful, or is this just random noise in my data? Variability starts to become an important thing, consideration when we're looking at particularly mean differences, a lot of the stuff that we're going to do in here this semester. If we have data with very low variability, it's going to be pretty easy to see patterns. If you see data with a great amount of variability, much more difficult to detect things, right? So if we look at experiment A and experiment B, which of these experiments do we have more variability, or are we seeing more variability, Nick?
Experiment B.
More variability here, right? If we look at within our group A, within our group B, we've got much more spreading out of scores, right? Versus these two. These are pretty tight, these are pretty tight, right? I would say I have less error in group 1 and group 2 in experiment A than I have in experiment B, all right? Whatever I've done, whatever my manipulation is to differentiate group A in my control, group B in my experimental group, I'm getting stuff that's all over the place. I'm getting things that are driving scores that go above and beyond the things that I'm sort of manipulating within the context of my study, right? And so it's going to be much easier to see, yeah, I see a systematic difference. It looks like group 1 is systematically lower than group 2. It's a lot more difficult to eyeball that with experiment B here. Okay. And so if we look at this graphically, right, this is experiment A. Low variability, not a ton of variability in terms of scores within my two conditions. And if I plot these two graphs out, again, mean of group 1 is 35, mean of group 40, difference of 5 points. Pretty easy to see that these two are different things, right? My distribution has very little overlap, but it's because my variability within my conditions is quite small, right? So we can see this, right? We can see, yeah, these are probably two different groups, correct? We agree on that? But how about this? Got a lot more variability here, right? Again, mean of group A is still 35, mean of group B is still 40. We've got a lot more variability. Our standard deviation in the last group is less than 1. Here, it's about 17, right? We still seeing a 5-point difference between these two groups. Am I as enthusiastic about saying that 5-point difference is meaningful in these two groups? Probably not, right? There's a ton of overlap. You're probably going to get chalked up to just sort of random variation here versus then it's right here, right? So if we've got data with a lot of variability in a group level analysis, it makes it hard to see these differences and test these differences versus when we have low levels of variability. Okay? That's not to say variability isn't bad. We need variability, particularly when we get into correlational types of stuff. Variability is important, but just from a means-based analysis, it starts to get more difficult to kind of see where things are at the more variable our data are. Okay. Questions about this? I'm picking this up, Sam? Perfect. Okay. Characteristics of standard deviation. Adding, subtracting the constant from each score in the distribution does not change our standard deviation, right? Changes our mean, doesn't change our standard deviation, right? If I have a set of scores and the mean is 10 and the standard deviation is 5, and I add 5 points to every score in the distribution, what's my new mean? What's my new mean? 5 points, so it's 15, right? What's my standard deviation? It's the same, right? I just took that distribution, I just shifted it over, right? The scores are all this, distance is all the same, right? So I can add, subtract constants for every score in this distribution. Doesn't change the standard deviation, but if I multiply or divide scores in the distribution by a constant, this causes the standard deviation to change by that level, right? So I've got scores where my mean is 100, or say my mean is 500, and my standard deviation is 50, right? And I divide all my scores in that distribution by 10. What's my new mean? My original mean was 500. Divided them all by 10. What is it? 50. What's my standard deviation? 5, right? So we go through, and so difference between our means, our standard deviations, determining whether or not we're adding or subtracting constants or multiplying, dividing, starts to switch things around a little bit. But it still does not change the shape of the distribution. It just sort of changes sort of the variability of scores there if we're multiplying or dividing by a constant. So things that can start to impact our variability, extreme scores. If we've got scores way out of bounds, right, way on the edges, that's going to impact our range, it's going to impact our variance, it's going to impact our standard deviation, all going to be influenced by these extreme values. What's not going to be influenced by extreme values?
Mode.
What's that?
Mode.
Mode, but if we're talking about our indices of variability that we talked about. Interquartile range going to be impacted by extreme values? Probably not, because we're chopping them off and just looking in the middle anyway, right? So that might be something you can think about looking at interquartile range. But range, standard deviation, variance, all going to be impacted by extreme values. Sample size, right? Range is going to increase with sample size. Why is this, Emilio?
Oh, because you can basically guess that with more sample, more extreme values you're going to get
right.
from the population.
The bigger my sample, if I got a big sample, I'm probably going to have some extreme values, right? And so as my sample gets bigger, I'm going to get closer and closer to my population in theory, right? I'm going to have a greater opportunity to grab those end values, and so my range is going to get bigger. But my variance, my standard deviation should remain relatively unaffected. Explain this to me. I'm getting more extreme scores. Why isn't my range or my standard deviation, my variance changing?
Because theoretically the mean shouldn't change, so the cutoff should be the same.
Okay, you kind of get in it. What's buffering? Yeah, Laura?
So I'm thinking that if you got like one more extreme score, that it's the deviation from the mean. So even though the mean shifts, it still sort of stays relatively the same from each data point.
Yeah.
As you add values, though, you're reducing your amount of error because you have a more stable sample.
Right.
So that should remain unaffected primarily unless it got smaller because you had better data.
Right. And so essentially what I'm going to do is, in order to get that extreme value, I had maybe 100 more people to my sample, and then I got that extreme value. But I also got 99 people who were still right there in the center, right? And so basically, with a larger sample, I have more opportunities to get more extreme values, right? And so my range, because my range is just built based on my largest and smallest the value, my range is going to get bigger. My variance and my standard deviation are going to remain pretty stable, because as I add additional values, where most of those values are going to fall? Right in the center, right? And so even though I'm getting more and more people in the sample, people I'm getting are probably going to be kind of in that sort of middle, sort of one standard deviation above or below. And so when I do hit that jackpot, like someone who's 7.6 or someone who's 4.10, that has less of an influence if I've got a lot of people in my sample as opposed to a small number of people. So stability, undersampling, range can fluctuate a whole lot, right? I pull one sample and then I pull another sample and then I do a third replication. Range is going to jump all over the place, right? But my variance, my standard deviation, going to remain relatively stable again, because my standard deviation, my variance, these are values that are calculated based on all observations and not just the two most extreme. So range is going to jump around. Variance and standard deviation are going to be fairly stable. But when we have open-ended distributions, right? If I have censored data, like how many miles am I driving in a given day, I can't calculate range, I can't calculate standard deviation, I can't calculate variance, because I need the actual values, right? I can calculate interquartile range, but I can't physically calculate a range, a standard deviation, or a variance estimate if I have censored data. okay? So again, things to be thinking about in terms of developing your studies, developing your research, thinking about impact of measurement and how that starts to influence things. Okay. Questions? Cool. All right. Variability in SPSS. Again, if we go analyze descriptives, frequencies, statistics, right? We can go through, we can calculate, ask it to give us standard deviation, variance, range. We can request quartiles up here. And this is what our output's going to look like, right? So we have, for these three variables that we've calculated here, we've got the number of people, the number of missing. For the people that we do have data for, here's standard deviation, here's variance, right? So if we take this and take the square root of that, what are we going to get? You think, Layla?
I'm sorry.
If I take the square root of that, what am I going to get? Oh, you don't have to run it through your calculator. My standard.
You're gonna get
Standard deviation, right? And you can go through and do that and check, right? Here's my range, 25th, 50th percentile. What's my 50th percentile, Laura? My median value, right? So we're pulling all this from SPSS for each one of our variables. One thing to think about, again, give you side eye on this, don't report things to 8 decimals, even if SPSS is giving it to you in 8 decimals. Don't report statistics to greater precision, right? I'm like to report a mean value on a Likert scale to like 5 decimals. It wasn't measured that precisely, right? So going through, and I'll help you sort of for things like effect sizes, we usually take that to a couple decimal places, right? After that, you're just adding digits just to add digits, right? So wanting to think about the precision of your estimates and things along those lines, right? Now, if I'm measuring things with a yardstick versus a micrometer, right? Sort of more significant digits there, but just please don't list things out to 4 digits just because it says so. But also don't report things in rounded whole numbers either, if it would be helpful to get some more precision there. Okay. Variability in data. Again, I can hit, we did this before, I can hit sum, caps, total, this is trait, STAI, state, trait, and then ask for stuff. I'm going to get my variance estimate here. You know, I can get my, calculate my range from my, I got largest and smallest values here, but we can go through and get some stuff here, or I could hit tab stat and sort of tell my variables and ask for mean, median, standard deviation, variance, range, count, all sorts of stuff that I wanted. It's going to give me sort of for each one of these. So here's my mean, my median, my standard deviation, my variance, my range, number of samples in there. So a couple different ways I can ask that. Yeah.
So the larger your standard deviation is